Okay, so this talk may seem a little out of place here, but I will start to give a motivation. So my group, we work a lot with machine learning and omics data. For example, we have a project where we predict the characteristic of different chemical components. We have several problems where we work combine machine learning and omics data in order to predict different types of cancer. We also work quite a lot with unsupervised classification with the aim to develop tools in order to identify novel subgroups of diseases. We also work with gene-gene interactions and develop methods for that with applications in plants, for example. So I thought a long time about what I should present today and decided that I should present something that is not really related to bioinformatics, but it's related to big data. It's related to how you can analyze big data, not only using machine learning, but also other types of approaches. And I think that this talk is fairly easy to understand, and I think it may give you some ideas how you can analyze genomics data as well. So this is the background. This is about pre-hospital care. So what you see here on the right is all the ambulance stations in northern Sweden. They are scheduled differently over time. At each station there can be several ambulances. So the question here is, how should we place our ambulances? How should we schedule our ambulances in order to reach the best pre-hospital care? So this is the problem. This is actually a very old problem, goes back 70 years ago or something like that. But today we have completely different tools, and in addition we have very different data. So within this project, that is a collaboration with all the regions in northern Sweden, we have all the alarm data for the last 10 years, and they are very detailed. We have the time of the alarm, we know who called, we know the whole pre-hospital chain, what happened. In addition, we have roadmaps describing the road net. We have demographic data describing detailed information about demographics in this area. We have meteorological data, and so on. So we have very big, very complex, and very unstructured data. So the whole idea here is that we try to use this data to model different parts of the pre-hospital chain. So for example, one thing we need to do is to model the distribution of the spatial temporal distribution of the alarms. We need to model the driving times, and so on and so on. So this is, in a way, traditional statistical modeling. This allows us to simulate data in a realistic way. So you can regard this modeling as a first step to construct a digital twin that in turn can be used to simulate realistic pre-hospital data. The input to this digital twin is that we may change our allocation of resources. So we may move some ambulances, we may schedule them in a different way. So given this change, we can do a simulation and look at the outcome. So generally speaking, the outcome will be some loss function that describes how well the quality of the pre-hospital care. So, and this digital twin is of course independent on what allocation we consider. There are numerous ways how we can allocate our resources. So we may regard each allocation as a design point in a high-dimensional space. And it's not hard to realize that for each ambulance, we have a lot of options. We have the when should the ambulance be scheduled, and that may vary between different weekdays, and so on and so on. So this is really indeed a very high dimensional space, and the aim here is to find the design point that minimizes the loss function. And in order to do that, we need to develop new optimization approaches that can handle this high dimensional space, in addition to the digital twin that may be regarded as a black box due to the complexity of the modeling. Okay, so I will give you some background and then I will return to this. So our study area is northern Sweden. As I mentioned, we have data, well, also almost 10 years. We have roughly in this area 100 alarms per year. We have around 70 ambulances and helicopters. Just to give you an idea of the cost here, the cost for operating one ambulance 24 hours, 7 days per week is approximately 10 million Swedish crowns per year. And again, the aim is to develop a tool that enable us to find the best way. We need to, of course, to define what we mean by that, the best way to place and schedule our ambulances. But before we start, I want to show you some real data. So what you have on the left here, the big picture, is actually, again, northern Sweden, and within each area here, you see the proportion of alarms, priority 1 alarm. So the alarms are divided in priority 1, that is really, really serious, priority 2, serious, and priority 3, basically things that can wait. So this is the data for priority 1, the most serious one. So you can see in this area, 59% of the alarms took more than 15 minutes. And interestingly, I think this part here is Umeå, and then you see that, this part here is Umeå, down here. Then you see that roughly 39% of the alarms are covered within 15 minutes. But you can also see that there are some places, Bjurholm, for example, where we have very low coverage. Only 2% of alarms are covered within 15 minutes. You can also see that if we look at the distribution between male and women, you see that it's fairly, you have age here, so it's fairly similar up to age 50, and after that the male will use more ambulances than women until we die, basically around 85 or 90 or something like that. Then women will have a higher load. If we look at the distribution between weekdays, it's fairly even, but within a day you see that by far most of the alarms occur during daytime and rather few during night. Okay, if we look at even more detail, this may be hard to see, but this is again what you have down here is Umeå, and this is red here means very long waiting times, green fairly short waiting times. So within the cities, Umeå, Skellefteå, Piteå, Piteå, Luleå, it's fairly short, but around is very long. If we look at Umeå in detail, you can see it depends how long you need to wait for an ambulance. It really depends where you live. So if you live in the center, it's very good. If you live a little outside, it may not be so good. So some words. Response time is the time it takes until the ambulance reaches the site of the alarm. So basically this is the time you need to wait. So the chain looks like this one. You call in, you request, and then SOS alarm 112 dispatch the alarm, and then the ambulance needs some time, a minute or so, before they can start driving. That's called preparation time. Then they drive to the patient. Then they treat the patient on site, and as they do that, they also select the destination, the hospital, where they will take the patient. Then they will drive to the destination, and then it takes some time to deliver the patient at the hospital, and then the ambulance is ready for the next mission. So basically, what we try to do here is to model all those steps and then do a big simulation. This is how it's done today. So this spot here, this is Umeå again, and this spot here is actually where we have the ambulance station today. It has usually 4 ambulances, and they are all placed here. So, and then we can see the coverage. So if you live basically within this red circle, then you will in average have an ambulance within 9 minutes. If you live further away, it will take longer. So one option here would of course be to move one of the ambulances from this place to some other place, for example this one. And if we do that, you see that we will expect to have a higher coverage and lower response times. And this is how it's done today. So you move and you put the circles around. Okay, so it's a fairly easy approach. Will it work? Well, unfortunately it will not work since it's not dynamic. So you realize after a while it doesn't matter how many ambulances you place on one station, since in this setup they will always assume that there is one ambulance at each station. And furthermore, it doesn't matter how you schedule the ambulances. And there are some other problems as well. So this was how it was done in the 50s, 60s, and so on, before we didn't have the data we do have today. So this is the idea we have. And it's not unique. I should say that other people are having similar approaches. So basically, so we define an allocation of the resources. We either use historical alarm or simulator alarms and take them one by one. We dispatch each alarm the same way as 112. We simulate all the actions the ambulance take, and we also calculate when the ambulance will be ready to take the next mission. And then we do this for 1 year of simulated data, and we repeat it several times as well. The good thing here, that given the time of alarm, given the place of the alarm, and given the priority of the alarm, this action can actually be assumed to be more or less independent. This enables us to do a simulation where we can simulate each part separately, which is the key here. So if, in general, if you have a problem that can be divided to sub-problems that roughly can be regarded as independent, then you have a much simpler problem that can be solved by solving each of the sub-problems. So the first step here is the first step is the statistical modeling. I will not go into any details, but we need to use spatial temporal methods to model the distribution of the alarms. We need to use some extreme value theory to model, for example, the treatment time of the patients and so on. We need to use some road database, some shorted path algorithms, some reduced graphs, together with some non-parametric regression to model the driving times. This is, in a way, the most tricky part, since it takes a lot of time to do these shortest path calculations, if you need to do it a lot of times. And in order to do them more quickly, we need to reduce our graphs. And we need a way to mimic how SOS alarm 112 dispatch the alarms. So this is the first step. Once we've done this, we can simulate realistic alarms, and without going into any detail, so we specify an allocation, our X value. We do simulation for one time period, usually 1 year. We simulate for the whole of Sweden, or in our case, the northern of Sweden. And we estimate some loss function. For example, in the simplest case, that will be the median response time, Y. And we repeat those simulations, for example, 100 times. So we get the point estimate of Y as well as the confidence interval for the expected value of this median response time. And now to what may be the most intriguing step here. So we have a digital twin that enables us to estimate Y with uncertainty for each user-defined X value, or X vector, where X is the defined resource allocation. As I mentioned at the very beginning, X here can be regarded as a design point in a high-dimensional space. If you think about it, it is really a high-dimensional space. It's several, independently how you define it, it's at least a few thousand dimensions here. The good thing is that we don't need to select all our X values at once. So we can select some X values, do the simulations, and get corresponding Y values. And based on those Y values, we can choose how to select the next set of X values. And we can do this in an iterative way. And this really help us to solve the optimization problem. Still, the problem is the dimension is too high, and in addition we have this black box property of the simulation that the standard theory, optimization theory, doesn't work very well. So we have proposed, together with Armin Eftekari, that is also a VASP recruit here in Umeå, a very nice and clever guy, also interested in collaborations within life science. So and an expert on machine learning. So this is a guy you can contact if you're interested in further collaboration as well. So together with Armin, we have developed a new optimization theory where we use stochastic derivative-free algorithms that search for a low-dimensional structure for black box problem. And I think this technique, together with this modeling, can actually be applied on a lot of problems. Okay, here one example we did. So today I mentioned in Umeå all 4 ambulances are placed here. We applied our simulation approach together with our optimization approach, and this is the suggestion. So today all 4 ambulances are placed here. The algorithm suggests that 1 ambulance should be placed here, 1 here, 1 here, and 1 here. So if we do that, still all the ambulances will actually be placed in the middle of Umeå, or fairly central. But if we do that, it will reduce the response time by little more than half a minute, or 8.8%. This is actually quite a lot. I mean, you don't need 4 new stations in order to do this. You only need to have a rule that tells the ambulances when they are free, they should go to those places, and the problem is solved. So you can see that we can reach rather big improvement with this small change. Okay, so thank you for your interest. And I don't know, is there time for a couple of questions?
Yes, I would say there's time. So. And thank you, Patrik. Yes, Paolo.
Thank you, Patrik. I love this presentation. I have a couple of questions. One is, you have all these sorts of data observations, data. Is there any problem with the privacy and sensitive data to actually use and process it? And then question number 2 is, I didn't quite get if these ambulances always have to go back to the base, to the starting point, or if they can hop from one service to another.
Yeah. So the first question, yes, there are a lot of issues with the privacy. And in order to use this,